This is a question taken from step 1. This is the first of 3 entrance exams that Cambridge require if you want to do maths at Cambridge. This will be significantly harder than the sort of questions you'll get in the book, but if you're interested in trying something a bit more challenging that makes use of the new differentiation techniques that you've learned, this will be a good one to get stuck into. There's a few useful things you can get from this, even if you don't manage to get all the way to the end without resorting to graphing software to help you out a little bit. If you would like a few hints, I'm going to put a couple of things up on the screen to help you. If you want to dive in first, now is a good time to pause. So here's some ideas of how you can get started. It's talking about a function x minus a over x minus b multiplied by e to the x. This is a typical step type problem where you've got a function that looks similar to things you might have dealt with before, perhaps a little more complicated, but instead of giving you a specific example, it gives you a more generalized form, and you need to say something about this family of functions by considering different conditions for the constants a and b inside. But you deal with it in the same way you normally would, so don't worry about a and b. Think of it as if they are just numbers you've not yet been told, and see how far you can get. So I would differentiate x minus a over x minus b first, because that piece is going to be necessary for the rest, but it in itself will require some careful work, so you might want to use quotient rule for that. And then you can get stuck into the main bulk of y equals something times something, so it's going to be a product rule situation. Once you've got that, because it's talking about stationary points, we're going to use dy by dx equals 0. And since it suggests there are 2 stationary points, that sounds a lot like there's going to be a quadratic involved, and you might have the opportunity to use the quadratic discriminant. Here's a few suggestions for when you get to the sketching graphs. This is quite a lot of stuff that you won't have covered in so much detail yet if you're just doing A-level maths. But if you're looking to move on to A-level further maths, you will cover these things in more detail and get more practice with them later. They're very useful skills to develop. So the first thing is, as you would normally expect, you try setting x equal to 0 to find the y-intercept if there is one, or more than one in some cases, or set y equal to 0 to find any roots, any places where the graph crosses the x-axis. You can also set the denominator equal to 0 in a question like this, where you are likely to have some vertical asymptotes, like it mentions in the first part 2i. You might want to look at when those occur by working out when the denominator will approach 0. And when I say test either side for that, we're talking about what happens when the denominator is close to 0 but not exactly equal to 0. There will be a value just to one side, just to the other, and that can give you a sense of what the function does, whether it goes up to positive infinity and then back down from positive infinity, like y equals 1 over x squared, or whether it goes up to positive infinity and back from negative infinity, like y equals tan x or something like that. Consider long-term behavior refers to what happens as x gets very large or x gets very low. In other words, large positive or large negative values, what will happen? And for this, it can be helpful to think in terms of the dominant function that you're dealing with. If you have e to the x involved, chances are that function is going to dominate in the long run. So no matter how good the other bit of the function is at keeping stuff small, if e to the x is trying to make stuff big, stuff's going to get big. And similarly, if we're talking about e to the power of a large negative number, that's going to shrink stuff so small that no matter how much the other function might be trying to make it big, e to the x is going to make it small. However, that only refers to the long-term behavior. In between, one of the other functions that's involved may well have some significant effect, particularly, for instance, at an asymptote. Doesn't matter how big or small e to the x is trying to be, if the other bit of it causes it to blow up to infinity or to shrink down to 0, then that's what the function is going to do. And finally, find the position of any stationary points. These give the added detail to a graph that is essential really for understanding exactly what's going on. Are there any maximums, minimums, perhaps even points of inflection? And if you need to, you can use the second derivative to determine the nature of the stationary points. That can sometimes be more bother than it's worth. Often, with a bit of careful thought and thinking about what's possible and what isn't possible, given what you know about the crossing points on the axes and the presence of any asymptotes, you can usually infer what the stationary points are going to be. For instance, with a cubic graph, you're expecting that you'll either have, for a positive cubic, let's say, you'll have a maximum followed by a minimum because of the nature of the graph, the way it's moving. Or if it's a negative, you might have a minimum followed by a maximum. The only case when that would break is if your two stationary points have merged into one and you've got a point of inflection like y equals x cubed itself. When you've had a go at this, continue with the video and I'll talk through my solution. So let's begin with x minus a over x minus b. We can use quotient rule to deal with this, and it might look a bit messy, but it's not too horrible. The numerator sorts itself out. I've used u so that I've got some letter I can refer to, but you don't have to explicitly state this. You can just refer to the derivative of x minus a over x minus b, or if you like, you can build it into the second part of the question here. We're going to deal with the next bit by using product rule. We can make use of our previous result, and I've written it in terms of u, but again, that's not essential. Done a little bit of simplifying after that. Remember, we've got the undifferentiated x minus a over x minus b multiplied by the differentiated e to the x, followed by the differentiated x minus a over x minus b multiplied by the undifferentiated e to the x. Of course, e to the x differentiates to e to the x, so that bit is going to be a factor of both and can be pulled out as a common factor, which I would recommend. There's more you can do to simplify that as well, but we're going to first notice that what we care about here is the stationary points, so let's set dy by dx equal to 0. In order to solve this, we could combine the two, put them as a single fraction, but it might be quicker just to multiply through both sides of the equation by x minus b squared. That'll deal with the denominator on both, and we'll end up with an additional x minus b factor for the left-hand fraction. We get this equation. This is the equation that must be satisfied by any x coordinates of stationary points. And, as we hoped, it is a quadratic. To see more clearly what's going on, it might help to expand it all out and look at it as a quadratic in its standard form. X squared, negative a plus b lots of x, and then the final bit is ab plus a minus b. And if we know that it has two stationary points, we can make use of the discriminant. I've used the triangle to represent the discriminant instead of writing b squared minus 4ac because I don't want to rename my a and b values, and yet there's no logical alternative to b and a and c for writing the discriminant unless I use a single symbol for it. You don't need to worry too much about that. You can just write discriminant positive, therefore, or something like that. Now, when we put this together, remember we're trying to end up with a minus b is less than 0 or a minus b is greater than 4. We're trying to end up with these. We know what we're trying to show, and that's really important. Whenever you get a bit stumped, think about where you're aiming for, and that'll help you to recalibrate your compass, if you like. So I've expanded this all out because I'm trying to see a way of turning it into something I can solve. But it involves a and b. Now here's where what you're trying to show can be useful. They're not asking us to say what is a, what is b. They're saying, can you find a condition for a minus b? It's a condition that involves both. So there must be something clever algebraically we can do here. By simplifying a little bit further, I can start to see why. The plus 2ab and the minus 4ab that we had on the previous line can be combined a little bit. And if we do that, instead of a squared add 2ab add b squared, we get a squared minus 2ab add b squared. And I'm already on the lookout for that because I've noticed that we have a minus b in both of the conditions we're aiming for. And hopefully you recognize that even though this involves a's and b's, which makes it in general quite hard to factorize, we can factorize expressions that involve two different variables, still technically a quadratic even if it has two variables, because the only time the terms appear it's in the form of either a or a squared, b or b squared. But we can factorize it. In the same way that a squared add 2ab add b squared came from a add b squared, a squared minus 2ab add b squared comes from a minus b squared. And I'm even more pleased that the remaining terms, minus 4a plus 4b, can also have a factor of a minus b pulled out of them. So this is just something you've got to spot. Doing a bit of rearranging will help, and looking at where you're trying to get to will help as well. So having factorized like that, we can pull out the a minus b as a common factor of both of those terms, leaving us with a minus b, take away 4. And now we essentially solve this in the same way we'd solve an ordinary quadratic inequality. If it said x multiplied by x minus 4 is greater than 0, we could solve that. We could think about the values of x for which this is true. Well, we just need to think of a minus b as its own variable. If it helps, replace it with something. Say let k equal a minus b, and then solve it as a quadratic inequality in k. When you've got your solutions for k, you've got your solutions for a minus b. The first thing we do with any inequality like this, we look for the critical values, and those will occur when either of the two brackets is equal to 0. And when we've identified those, we can think about the nature of the quadratic itself and ask when it will be positive. You might do it with a quick sketch. You might just notice that it's a positive quadratic. If it was k times k minus 4, that's a positive quadratic, which means if we want to know when that quadratic is going to give a value greater than 0, it happens either side of the two stationary points, either side of the two critical values, rather than in between the two critical values. And that's the result we were asked to prove. That, believe it or not, is not even part I of the question. That is the preliminary bit, the precursor. But it's there not just to slow you down before you get to the good stuff. It's there to help you with the next two parts. The idea is you can make use of what you've done here to help you with the two sketches that are coming up in parts I and II. So let's look at part I. We've already got some information here. We're trying to answer a question involving stationary points on either side of the asymptote. So let's think about the stationary points and let's think about the asymptote. The stationary points, we already have this equation. That's the one that we worked with and found a condition involving the discriminant for previously. But we can now substitute in specific values for a and b. That gives us a quadratic we can solve. You can do that any way you like. I've completed the square because remember with a step paper you're not going to have a calculator, so it helps to build a bit of fluency dealing with quadratics like this. You should get nice enough answers, and of course if you want to you could just multiply through by 2 and factorize things. I've got values of 1 and minus a half for x. That shows me that the stationary points occur when x equals 1 or when x equals minus a half. All I need to do now is figure out where the vertical asymptote occurs. And that will happen when the denominator of the fraction is equal to 0. So if we look back at the original curve that we're dealing with, which will be y equals x minus nothing over x minus a half, multiplied by e to the x, the denominator is x minus a half, which means the vertical asymptote will occur when x minus a half is 0. So when x equals a half. And that fits. We've got an asymptote when x equals a half, and then to the left of that we've got a stationary point at x equals minus a half, and just to the right we've got another stationary point when x equals 1. And the last bit, this throwaway comment, oh, and by the way, sketch the curve please. So the previous part is leading up to this, it's helping you to get some additional information that you'll be able to make use of. And although I can't demonstrate very well on the board here exactly how I would scribble down various sketches, I would usually have 2 or 3 different drafts as I make my way towards the final sketch. I'd mark on the information I have and make some intelligent guesses about what might be happening elsewhere and then investigate further. I'm going to try to represent some of the working out that goes along with this, and we'll try to make it into a reasonably formulaic process that you could do for most functions you might need to graph. So we're going to look at what happens when y equals 0 for a start. If we want to know when y equals 0, well, we're not going to get any joy from looking at the e to the x factor because e to the x is never 0. So we look at the other bit, and that will be x minus a over x minus b equals 0. Well, the denominator doesn't help us there, so we focus on the numerator. X minus a equals 0, so x must equal a, and in this case a is 0. We also have some useful information here. E to the x is greater than 0 for all values of x, and x over x minus a half is positive if x is big enough. Think about 1,000 over 1,000 minus a half, or if x is small enough, negative 1,000 over negative 1,000 and a half. but it's going to be negative if just one of those two terms is negative. So somewhere in between 0 and a half, for instance, if you think of x being a quarter, you'll have a quarter on the top, but minus a quarter on the bottom. You can investigate this using critical values in the same way that you can with quadratic inequalities. All we care about is whether the top and the bottom will both be positive or both negative or one of each. And the only time that changes is when one or other of those two terms, x or x minus a half, switches sign. That happens when x is 0, when the numerator is 0, and when x minus a half is 0, when the denominator is 0. So test those two, consider what happens in between, and consider what happens either side, and we can see that we're going to get negative values for that fraction when x is between 0 and a half. We've also got this information that e to the x shrinks towards 0 as x tends towards negative infinity. So as you move towards the left, this graph is going to be pulled down to the x-axis. And it never quite reaches it because e to the x tends to 0 but is never going to be equal to 0. Now, here's a nice way to think about what happens either side of an asymptote. We already know there's an asymptote at x equals a half. So let's think about a half minus a small number. Now I've used epsilon here. So it's a standard approach for university maths, but you don't need to be put off by it too much. If we try a half minus a small amount, and you can just try literally a small amount here, try 0.01 or something and think about what's going to happen. We have something just less than a half on the top of the fraction and something just less than 0 on the bottom of the fraction. In other words, a positive over a negative. So it's going to be negative. And just above the vertical asymptote, we have a half plus a bit over a bit. Both positive, therefore will be positive to the right of the vertical asymptote. So what we're saying here is, as we approach the vertical asymptote, we're going to be negative on the left, positive on the right. That must mean we go down towards negative infinity as we approach from the left, and we come back from positive infinity. So here's my final verdict. Y approaches the x-axis from above as we move towards the left, as x approaches negative infinity. But as we move towards the right from negative infinity, we increase to a local maximum at x equals minus a half. We can sub that into the original curve to get the y coordinate as well and verify for ourselves that that is a positive value. And then it drops down through the point 0, 0. That's the point we found originally when we thought about what happens when y is 0. And then it approaches negative infinity at the vertical asymptote. The vertical asymptote has equation x equals a half. And then it returns from positive infinity on the other side of that discontinuity, the vertical asymptote, and it comes down to a local minimum at the point 1, 2e, 2e to the 1. And finally, it tends to positive infinity as x gets bigger and bigger. Our function is also going to get bigger and bigger. And it will end up looking more and more like the graph of e to the x. It'll be a convex graph, increasing at an increasing rate. Now I'm going to cheat and show you the GeoGebra graph. This is what it should look like. It doesn't matter if your graph has a different sort of scale. What matters is that you've got the overall sense of the graph. You've got the key features, you've identified the asymptotes, you've got the coordinates of the stationary points, and you know where it crosses the axes. Let's look at the second part now. They're giving us different values for A and B, and you might want to stop and think at this point. The first part of the question gave us a value of A that was 0 and B that was a half. In other words, a value of A that was less than the value of B, something which satisfies the first of the two conditions that we found at the very beginning. Now we're being asked to deal with a situation where A is 4.5 and B is 0. In other words, where A is at least 4 bigger than B. That's something that satisfies the second condition we found. So these are two distinct conditions. You can either satisfy the first or the second, but not both. So this will be a different sort of graph. It's going to be also a graph with two stationary points, but the nature of that graph may be different. There's a clue here that in the first part of the question it says, show that there's one stationary point on either side of the vertical asymptote. With this one, I suspect we'll find that there are still two stationary points, as we showed at the very beginning, but perhaps they won't be on either side of the vertical asymptote. So that's what I'm looking out for. The first thing to do, I'm going to do here, this is a little different. This is modeling for you a slightly different approach to sketching the graph. I'm going to look exclusively at this first piece, the x minus a over x minus b bit of the curve. If I can sketch this, which should be fairly quick, it's not a particularly complicated one, it's a transformed version of effectively the y equals 1 over x graph. But if we can sketch this one, we can then think about how it will be modified by being multiplied by e to the x. So we'll start by looking at where it crosses the x-axis by setting y equal to 0. That means the numerator will be 0, so we get x minus 4.5 is equal to 0. And I've also made a note that to the left of that point, it's going to be negative. It'll be below the x-axis, and to the right, it'll be positive above the x-axis. You can see that just by thinking about values of x that are not equal to 9 over 2, but perhaps just slightly lower. If you start with, say, 4.4, instead of 4.5, you'll have 4.4 minus 4.5 over 4.4. In other words, a negative over a positive. Whereas if you have 4.6, then you end up with a positive, small positive on the top of the fraction and a positive value on the bottom of the fraction. So we know not only that the curve crosses the x-axis at this particular point, at the point 4.5, 0, but also that it's crossing from below to above as we move to the right. We can do a similar thing with the asymptote. So we can see by setting the denominator to 0 where the vertical asymptote occurs. But by looking at a value just to the left, like minus 0.1, and a value just to the right, like positive 0.1, you can fairly quickly see that this graph is going to be positive just to the left of the vertical asymptote and negative just to the right. In other words, it shoots up towards positive infinity as we move from left to right, and then after the asymptote comes back from negative infinity, does the wraparound. And finally, the long-term behavior of this graph. What happens as x gets very large and what happens as x gets very small? A really neat trick here is to divide the top and bottom of your fraction by x, or for more complicated ones, by the highest power of x that appears. Because what that does is it changes everywhere where x appears into a fraction where x is a denominator. And then you can make x as big as you like, and all that will happen is those fractions where x is a denominator will shrink to 0. And you can see that the leading term, the number in front of x, is the thing that eventually determines where this thing is going to go. We've got x plus or minus something over x plus or minus something, which means in the long run, we're going to be ending up with a y value which is equal to the ratio of 1 to 1. If we had y equals 2x plus 7 over 3x minus 14, we would end up approaching 2 over 3, because in the long run, the bit of the function that has the most significant impact is the most significant bit of the function. If it's a linear function, that means the x bit of it. If it was quadratic, then the constant is insignificant compared to the x term when x is very large, but by the same token, the x term is insignificant compared to the quadratic term when x is very large. So the bit that determines the long-term behavior will be the most significant or the hardest hitting part of the function. So we can see that we get a horizontal asymptote here. They're a little different to vertical asymptotes. Vertical asymptote is more like a discontinuity, a break, a point where the function can't exist and we can analyze what happens either side. A horizontal asymptote is not necessarily a line that can never be crossed. It's not like we can never get a y value of 1, but it's more like showing us where the curve is getting closer and closer to as x increases without limit or decreases without limit. So we can now sketch the curve. It looks like a version of y equals 1 over x with a few little tweaks and changes. We can see the vertical asymptote is the y-axis, the horizontal asymptote at y equals 1, and we can also see that it crosses the x-axis at 4.5. So we've got that information to start with, and it's remarkably straightforward from that point on, give or take a few wiggles, to think about what happens when we multiply by e to the x. To start with, all that tricky nonsense we had to think about with is it positive, is it negative, is it 0, all of that is taken care of for us because e to the x is always positive for any value of x. And therefore, whatever this reciprocal graph does, the graph of the reciprocal multiplied by e to the x will do the same thing sign-wise. When the purple graph is positive, the purple graph multiplied by e to the x will be positive. When the purple graph is negative, y, our curve, will be negative. And when the purple graph is 0, our curve will be 0. Not only that, but wherever our curve has an asymptote, whenever our curve is undefined, then our curve, wherever the purple graph is undefined, our curve y equals reciprocal graph multiplied by e to the x will also be undefined. So all of that is incorporated in our thing. Same vertical asymptote, same behavior either side, because we can even see at the asymptote, does e to the x do anything crazy? No, e to the x is approximately 1. It's a little less than 1, moving to a little more than 1. But when x is about 0, then e to the x is about 1, and it's not going to break the asymptotic behavior at that point. The signs and the root match this graph, so we have the same 0, the same positive bits, the same negative bits, and we also know that e to the x dominates for very high or very low values of x, which is important here because as we move to the left, instead of approaching a value of 1, we approach a value of 1 multiplied by e to the power of a large negative number. So the 1 doesn't really determine where the curve ends up in the long run. What determines where it ends up is e to the power of x. And similarly at the other side, instead of tending towards y equals 1, we tend towards y equals 1 times e to the power of an increasingly large number. In other words, we don't tend towards a fixed limit at all, we approach infinity. So our curve is going to tend towards 0 as we go to the left, and it's going to increase without limit as we go to the right. The last thing to notice is what this question started us out with, the stationary points. Because although we've got a sense of what the sign is for our graph, we don't know about any wiggles and bumps that might occur along the way. So we need to think about the fact that, well, we satisfy one of the conditions, a minus b is greater than 4, therefore there must be 2 stationary points. We just have to figure out where they are. Now, if you look at the purple graph we've drawn, you might be able to have an intelligent guess at this point where you think the wiggles might occur. But it should be clear, if you spend enough time thinking about it, that they cannot occur either side of the vertical asymptote. If you have a maximum and a minimum, and yet the graph is supposed to continually increase, it can't have what am I trying to say? If we have a maximum and a minimum before the asymptote, that could work. You could have a wiggle, just like a y equals x cubed graph has a wiggle. Or you could have a maximum and a minimum after the vertical asymptote, and that could work. But if you have a maximum before the asymptote and a minimum afterwards, or something like that, you find it doesn't quite fit with what we're seeing here. Think about where the asymptote goes and where it crosses. And if you try drawing a few versions of this, try putting your stationary points in different places and thinking about what their nature would have to be, you'll see that it only makes sense for us to have 2 stationary points on one side or the other of the asymptote. That's a little hard to get your head around though, and I've obviously made a bit of a hash of explaining it. So what I would do if I were writing this down for myself after trying to play around with it is to get stuck into a little bit of algebra. Come back and we remind ourselves that we can work out not only where the stationary points should be relative to the vertical asymptote, but we can work out exactly where they should be because we've got an equation for it. We go back to the equation we had right at the very, somewhere in part I, where we'd had x minus a multiplied by x minus b, take away a minus b or plus a minus b, something like that. And if we put our values into that, we can solve it. Again, I've used completing the square. You can use whatever method is most convenient for you. And I've got 3 and 1.5. So those are the x coordinates of my stationary points. We can now look at the graph we've currently got for the reciprocal part of our curve, and we can see that 1.5 occurs to the right of the vertical asymptote, and then 3 occurs to the right as well. Both of those happen before the point 4.50, where the graph crosses the x-axis. So whatever wiggle is going on happens before the x-axis crossing point. And finally, the curve increases without limit and also without any stationary points after that point, after the 4.50 point. So we know that it's not going to have a high point and dip back down or anything after that point. Therefore, it's just going to continue to rise beyond there. The points that we're interested in at 3 and 3/2, they must be firstly a maximum followed by a minimum. So at x equals 1.5, we'll have a maximum point. The curve comes up from negative infinity, peaks temporarily, dips down, has a minimum, and then continues on its way up until it reaches its 0 at 4.5, 0, and then will continue upwards to positive infinity. And here's what our graph looks like. You can see the little wiggle just down at the bottom. And I've left on the purple graph the reciprocal graph so you can see how the sign of our graph always matches the sign of the purple graph. And the zeros of our graph match the zeros of the purple graph. And the vertical asymptote of our graph matches the vertical asymptote of the purple graph. So the general behavior in terms of positive, negative, 0, that matches the graph that we had multiplied by e to the x. That's why this can be a really useful method. You've got two functions that you understand fairly well. When you multiply them together, you can often infer quite a lot about the behavior of the product of the two functions. If you're interested in seeing a bit more of what's going on behind the scenes, GeoGebra is a great way to investigate further. So if you start up your calculator and we just type in exactly what was given in the question, we can play with the values of a and b as they appear. So y equals x minus a over x minus b, or multiplied by e to the power of x. Now pops a graph that should look familiar. That looks like a straightforward exponential graph. And of course it is, because at the moment x and b are the same value. They've defaulted to 1, but they don't have to stay that way. We can change the value of b by messing with the slider. If we set b equal to 0, then we get this interesting situation where in the long run, this still looks kind of like an exponential graph. In fact, you can even plot y equals e to the x on the same set of axes and observe how the long-term behavior of our graph is basically the same as the long-term behavior of e to the x. We can also look at the other function that's messing things around. So that's the x minus a over x minus b function, and see how both of those are coming into play here. The e to the x function is the deciding factor when x is very large or very low, high positive or high negative, but the reciprocal graph x minus 1 over x in this case, that has the deciding, the last word if you like, when x is very close to the asymptote. So e to the x doesn't play much of a role when x is close to 0, but x minus 1 over x is going to blow up to either positive or negative infinity, so that definitely rips a hole in the e to the x function. We can play with different values of b, and you'll see how things change around at a certain point. Those points are worth noticing. If we try to catch it at one of them, what's special about this point is that the value of b is very similar to the value of a. That's why in the original question, they were talking about a minus b. The conditions that we found for two stationary points were a minus b is less than 0 or a minus b is greater than 4. In other words, either a has got to be less than b, which is what happens if we drop a to being a slightly lower value, or a has to be significantly bigger than b. So make a so much bigger than b that we get two stationary points again. Don't forget the main function we're interested in is this one. I might make that a bit bolder so we can see exactly what's going on. The two stationary points we found in the second part of the question will have been these two. That's what happens in the cases where a is a lot bigger than b. And you can see if we mess with the value of b, all we get is a more extreme version of these. That function there is still emulating y equals e to the x in the long run. It's hard to tell. The asymptotes go a little crazy on GeoGebra after a while. But in the long run, this graph is going to look like the blue exponential graph. But in the short term, when we're close to the asymptote of the reciprocal graph, we're going to see the nature of the reciprocal graph asserting itself a little bit more. You see when a and b start to get more and more similar, we're going to end up reaching a point where things switch around. But once we switch around, once b is larger than a, we will end up again with two stationary points, but this time it's more like the situation in the first part of the question, where the first stationary point is on the left of the asymptote and the next one is on the right. We can mark on the asymptote if we like. That's going to happen when x equals b, so we can just type x equals b, and if we don't want to make that too distracting, we can make it a dotted line, turn it grey, whatever you need. And you can just sit and play with it for a bit. I recommend you try building this for yourself. You look at what happens as A and B both change. If it gets too cluttered, you can lose some of the graphs. See if you can make sense of the whys and wherefores. And a good way to do that is to draw the functions that go into making this function, and to look at which graph is what in the long run and which graph is what in the short term. So when you look at certain places, different functions will have the last word in terms of what the eventual function will do. Have a play around, see how you get on.